Okay, without further ado, welcome all to this month's our Met's local South East Centre meeting. We have a very exciting talk from Humberley today, but before we get started, we have our weather overlook by Rob Thompson. So
Cheeky sneak the weather summary. Talk a little bit about the autumn we've had and a little bit about not the autumn we've had. And it looks like we've got the magic automatically updating slides, which is not maddening for Izzy at all. We can actually go forward now. Possibly too. So I thought I'd start by looking at the in Reading. This is fun, definitely not going to be long. Meteorological calendar. So so far in 2023, we've had 773.8 millimetres of rain in Reading, which makes it that if you're measuring your date by rain, because that's always a good way to measure the date, it's already past the end of the year and into next year. So yeah, basically we're already past average annual rainfall. The 5th of December in sun, we're actually slightly sunnier than average already, and our thermal days are well ahead as well, which probably isn't surprising to anybody in this room that we're warmer than average. But if we go on, I thought since we've said that, I'll look at the rain in Reading. So this is our sort of accumulating rain and monthly rain totals for 2023. And I've put inside a little sort of chart of how much we've had and the anomaly on each of those. And I've listed November as if this was the end of November and then a month so far compared to what you would expect to the 14th. So even if it doesn't rain again in November, we're still on 89% of normal, but it's going to. And yeah, so we're plus 92% compared to where we should be halfway through November. But I think what really strikes on here is we had a drought where February was the driest February on our record, then followed by the wettest March on our record, and really it didn't give up doing what March did, pretty much. So every single month since February has been wetter than average, and November almost certainly will be when that's all through. So that's our year with rain. Thought I'd look at a little bit at the temperatures. So these are sort of maxes and mins through the year. It's really nothing greatly strikes me. And this doesn't actually strike me as especially special, but I'm not sure this came up in WCD even for the WCD regulars. That, you may notice, is dropped below the freezing point. So if we click onto the next one, that is, I made this chart from the university's field site, and every time this goes so back to 1908. This is the day of the first air frost of any given winter. And so that was 2023. So compared to the long history, it's not particularly unusual, but that was the earliest air frost this millennium. The last time there was one earlier was 1999. So that was actually unusually early. As a gardener, it killed my runner beans. It's a bit late anyway, so it wasn't too much of a problem, but that was a surprisingly early air frost. It didn't really hang around, that cold snap. It lasted one night, and we've had two more since. But yeah, that's so, but quite different from last year where we were into December before we had the first air frost, and that went straight into a very cold snap. So quite different. But, yeah, move on, we'll go a bit more national, look at sort of the autumn's rain so far. So we have the anomaly charts for September and October. September, on average, is a bit wet, but it's quite patchy, really. Mostly convective stuff, and basically a big heavy shower goes there, and like a few showers go there, etc. October is just wet, basically. You've got the systems that went this way, and of course, lots up on the sort of Scotland east coast, particularly. And then this was Storm Babette, and the 18th to 21st of October, how much rain fell. That's the total, and that's the percentage anomaly, and just an enormous amount on that patch that had the red warning of rain there. So over 200 millimetres in 3 days is pretty spectacular amount of rain. But actually, those anomalies were huge over the east of England as well. So a massive amount of rain in just 3 days. And to some extent, if you actually look at that chart and compare it to that chart, kind of shows you how much of that rain was all in one storm. In that they've certainly got the same kind of pattern in a fairly large scale. So, I guess that's the classic case of the Daily Mail headline of 2 weeks rain in one day, which actually isn't as unusual as you'd think. So this time it was probably 2 months rainfall in one day, and that then it really does show up on the anomaly charts quite clearly. We click on. As I just said, the press office messaged me saying, "Oh, 4 named storms by now, unusual." Well, I wrote this 2 hours before they sent me that message with, "We've had 4 named storms, is that unusual?" I guess the answer to this is there's not actually that much precedent for naming storms. What, 10 years now, Humphrey, something of that ballpark? And so while it probably is the most by mid-November, I'm not sure in a 10-year record that means all that much. But we've had Agnes, Bet, Kyron, I assume it's pronounced Debbie, that have all been, it looked like that was actually doing more than I thought it might. But I guess going through the north, we don't really see much of it. Whereas, obviously, they had the fairly significant tornado on Kyron. So having an office mate from Jersey does give me top secret access to information about Jersey. So if we move on, I've got my last slide. I thought it was important really to show the global picture slide. So this was September and October's global temperature anomalies, both of which are just massively higher than anything previous. I'm not 100% sure why. I've heard of quite a few theories as to why, but there's a big step, and it's not like it's just suddenly September was way higher than everything else. August was a fair chunk higher, July was higher, etc. So they have fed it in. And then October's not quite as extremely higher before. There's a few other interesting things you can see in here, actually. Some of the quite big sudden drops, like this one, they're volcanoes. So you can spot the volcanoes in here. That one's Pinatubo that I pointed out. So you can spot the volcanoes, but you don't really get the big jumps up. So that's an interesting one. But it looks now we're very, very likely to get the hottest year on record. Or record if you lose the O off the side of my slide, and almost certainly to be plus 1.5 over pre-industrial average as well. So a kind of big Paris Agreement problem again. So that's my global temperature picture. I'll give back to Izzy to introduce Humphrey properly.
Thanks so much, Rob. Next up we have Green talking about the WesCon project. I'll let you talk about it.
Thanks very much, Izzy, and thanks for the invitation to talk. Pause. Right, excellent. So yes, so WesCon I'm going to be talking about today. I think it goes without saying. Oh, we've lost the edge of the slide. It goes without saying that this is the work of a huge number of people, many of whom are possibly in the room or online. So I'm kind of representing a work of many people. This isn't all my work, obviously. So move on to the next slide. So plan of the talk. So I'm going to give a bit of an introduction to the modelling systems we use and how they represent convection, which is the subject of interest in this. And then I'll say a bit about the motivations for WesCon, which come from that. And then I'll introduce the campaign a bit, and then I'll say a bit about some of the observations in a bit more detail and give some examples of the sorts of results we're getting, what we got, and then say a bit about the modelling we did around WesCon and the UK testbed, and then finally a bit about next steps. So we move on. So the motivation of WesCon is that convection is a very important forecasting problem in the UK and generally in the world. It's something that we really care about. It's something that the forecasters don't want to get wrong. So, I mean, obviously, this was the Boscastle flood. There's been many other famous floods caused by convective storms. And so, yeah, it's something that we care about in the Met Office and we want to improve. A key aspect of improving the model forecast is observations of real convection. And I'll say more about that in a little while to justify that comment. But that's kind of the motivation for doing a field campaign to look at convection. And the bottom line is that routine observations that we have every day as part of the modelling system and part of just the observing network are not sufficient to help improve the model. So we need bespoke observations in a field campaign. So that's the motivation for doing field campaigns. So next slide. So I thought I'd start off by introducing the modelling system we use. So in order to forecast the weather and the climate for that matter, we use models of the atmosphere, computer models. And the models work by solving the equations of motion and thermodynamics, etc., on a grid, both horizontal and vertical. And the size of the grid is an important parameter of the model. So there's a trade-off. So if you make the grid much finer, you can resolve much more detailed things in the atmosphere. On the other side of it is that the model gets much, much more expensive. So there's a very practical trade-off. So this is a summary of the NWP configuration at the Met Office for forecasting for the UK. So we start off with we run a global model over the whole world, which has a 10-kilometre grid length. And that runs out 6-day forecast twice a day. So that's one of the workhorses for forecasting that the operational meteorologists use. So if we go to the next slide, this is just an example of the sort of thing that you get. This is, I just pulled this off. This is the forecast for either tonight or tomorrow or something. So this is the sort of thing you get from the global model. So it does very well for the sort of slightly larger scale features. So this is the size of the UK. We've got various low pressure areas, etc. So if we move on to the next slide, so we also run a more detailed model specifically for the UK called the UKV. Ignore the Euro 4, by the way. It's quite an old slide. I couldn't find a newer version. The Euro 4 has actually been turned off now. It took a very long time to go, but it's gone now. So the UKV is a 1.5 kilometre model. So the grid boxes are 1.5 kilometre in size. And that runs out to 5 days, twice a day, and then various other sort of runs out every hour, runs out for about 12 hours for shorter range forecasting. So if we go to the next slide, so this is the domain of the UKV. So the V stands for variable resolution. So the domain, the middle bit of it, is this bit which covers Great Britain and Ireland. And you can see that, this is the area of the 1.5 kilometre grid. And then that grid stretches as you go out towards the edge of the domain, which is why, as I say, why it's called variable resolution. And the boundary conditions for this model are obtained from the global model. So the overall weather situation and when sort of lows and things come in comes from the global model. Okay, so next slide. So the question is, we're obviously talking here about forecasting convection. So how do the models cope with convection? So this is a schematic. So there's an important distinction between how the different models cope with convection. So the global model has a 10-kilometre grid. So the schematic here, we've got a sort of convective cloud, which is smaller than 10 kilometres. And this is the size of the grid square. So it's completely obvious that you can't represent this cloud properly with this model. You can't resolve it at all. And so instead of that, the model has what we call a parameterization, which is essentially, it's a piece of code which looks at the model profile and it decides whether there should be convection on that grid box. And then it modifies the model fields according to whether it thinks there's convection. And it also produces cloud and rain that represents the convection. So it's not explicitly representing the cloud, but the parameterization is kind of doing the job of the cloud, of the convection. So if we contrast that with the 1.5 kilometre model, then you can see that this is obviously very approximate. It depends how big your cloud is, etc. There's a big range of sizes of clouds, which is part of the problem. But you can see that you're getting several grid boxes in your cloud, and so you do have a hope of actually representing that explicitly. So sort of the updraft in the cloud, which is causing condensation, etc., in the convection, can be represented probably to some degree in the 1.5 kilometre model. And so, as I'll show in a minute, this gives many benefits, but still needs improvement. So that's why we use 1.5. One of the drivers for going to kilometre scale models, as we call 1.5 kilometre model and similar models, is that we can then go to get better representation of convection. So if you move to the next slide, so this is an example. This is from a review paper we wrote a few years ago. So this is an example where there's a showery day over the UK, lots of convection going on all over the place. And this is what the sort of thing the global model does. So this was, again, this is slightly out of date. It was, when we wrote the paper, it was 25 kilometres, but even when it's 10 kilometres, the same thing holds. So you can see that what you have here is, we're not generating convection that looks very realistic, but the convection parameterization in the global model is giving a good indication generally of the areas where there's going to be convection. Of course, forecasters would look at that and they'd look at the profiles and they could say quite a lot about what the convection would actually be like in practice. So if you contrast that with the 1.5 kilometre model, then you can see quite nicely that there's sort of a good much more realistic looking representation of the convection. So you can sort of start to see features like that looks quite similar, etc. So when these models first came in, everyone thought they were brilliant. They're much better, and to this day, obviously, 1.5 kilometre model is one of the workhorses for forecasting for the UK. So next slide. The other, just as a side note, just to make a comment about ensembles, that one of the problems with forecasting convection is it's a chaotic process. So you're never going to get all the little individual convective cells in exactly the right place. So in order to cope with that, we run the model a number of times with slightly different starting conditions. And because it's a chaotic system, starting conditions and also different boundaries and different physics sometimes. And so this is just an example where there's 4 members of an ensemble. We've actually run a lot more than that. This is the 2.2 kilometre ensemble, which is kind of the ensemble equivalent of the UKV that we run. And you can see here that we have, you know, each one of these is kind of giving something vaguely similar to that, but not the same in detail. But then if you go to the next slide, what we do is we then process all the members into a probability. And so what you then get is you get a nice kind of, and you can see in this case, it's done quite well here, that you've got quite a nice representation that there's going to be this is the probability of having over 8 millimeters now, which is kind of the red here. So you can see it's picking up this quite well, but maybe down here it's not doing quite as well. But that's why we run ensembles. It's just a sort of side note which will be relevant later. So if we move on. So as I said, the kilometre scale models like the UKV have, you know, they've been running for about 15 years now, etc. And so they are used a great deal in practice for forecasting and particularly for looking at convection. But there are problems with them. So, I mean, if you ignore the middle picture here, this is the 1.5 kilometre model, and this is the equivalent radar picture. And you can see that there's some pretty serious sort of biases, that you've got too much heavy rain, not enough light rain, so there's too many reds and not enough blues. And also the cells are rather too big. And it's a technical term we use, we call them blobby. The cells are a bit too blobby. And we believe that fundamentally, the reason for this is that we're still under-resolved in a lot of cases in the UK. So this is a bit of work that someone did a long time ago, who just looked at the radar over a whole load of cases and saw the average sort of radius, diameter rather, of the storm for different thresholds. And you can see for 1 millimetre an hour threshold, the average storm is about 4 kilometres wide. And if you've got 1.5 kilometre grid, you're obviously not really going to resolve that problem, particularly when you're trying to resolve the updrafts in there. And so, as I say, we believe that the real fundamental problem there is that the convection is too small to be represented in many cases. And so we need a convection parameterization that works at kilometre scales, but we need a clever one that can do it without destroying the benefits that we've got from doing some of the convection explicitly, particularly when it gets larger. And so that's what's called a grey zone parameterization, because grey zone is you're neither in the regime where you're completely happy to parameterize everything or you're completely resolving it. And so the idea would be we need a scheme which will correctly represent small showers while still giving the benefits of explicit representation when the storms get a little bit bigger. And so developing a grey zone parameterization for kilometre scale models is one of the key things that we're expecting that WesCon will help with in terms of the observations. And I'll say more about that in a minute. So if we move on a bit more, the other thing we're interested in is I lead a project to go to much higher resolutions. So the Met Office has got a project to develop sort of 100 metre scale models, which of course is even finer still. So we tend to call those urban scale models, and that's kind of analogous to sort of saying convective scale models, the kilometre scale models. But the important thing to note is that doesn't exclude non-city applications. So for example, if you're looking at storms over southern England, then that's not necessarily urban. So this is just a comparison of, for London, for example, how much more detail you can see in a 100 metre model compared with a 1.5 kilometre model. So if we go to the next slide. So if we think about convection, then when we run our models with much higher resolution, then some things do automatically kind of improve with the current models that we have. So this is the radar composite again. And now if we go to 100 metres, and that's what we had before, the 1.5 kilometre, we now see that we do a lot better. So, you know, the general balance of reds and blues, so the heavy rain versus light rain is a lot better. And the general scales here are a lot better, but you might notice that we do see a lot of extra spurious cells there. So that is a known problem. So there's a lot, this is the list we have of all the problems with convection in the 100 metre models. And these are the things that we would like to be able to improve, and WesCon is part of that. So yeah, the other key thing is that when you go to 100 metres, of course, you've got a lot more scope to resolve thunderstorms and clouds. So you really need to be clear that the better resolved structures are actually realistic, rather than doing just something on its own that's very unrealistic. So if we move to the next slide. So if we go back to my schematic, now if we go to much higher resolution, then you're more confident you can resolve, for example, the updrafts in the storm. We don't really know exactly how wide they are in this case because it's a schematic. But the other thing is, what we believe is important is the turbulence at the edge of the updraft, so the detrainment or the entrainment of air into the updraft. And so that is then represented you need some kind of way of representing the turbulence. And so the point about going to much higher resolution is that you start to resolve some of the turbulence. And so you really need, again, analogous to the convection scheme that I talked about, you need a grey zone turbulence scheme. And so it's very important to understand the updraft and the turbulence in these clouds to really understand how you're going to represent them in 100-meter scale models. So if we go to the next slide. Here we go. So as I mentioned, one of the issues which we are trying to look at with WesCon is that when you go to very high resolution, you see a lot of small speckly showers. And this is an example of that. So the network radar had almost no showers at all in Eastern England in this case. And yet some of the 100-meter models had quite a lot of showers. But when we look at the actual cloud, then the cloud actually, so there's these convergence lines here, the cloud actually looks reasonably realistic. And so we believe that the problem with too many showers is that the clouds are not so bad, but they are precipitating spuriously. And so, as I say, this is one of the things that we really want to get to try and understand. So if we move to the next slide. So just for a bit of background, so we have been playing, despite these issues, with a 300-meter ensemble. And one of the reasons that we're interested in doing this is this does look very, very promising. So this is something that Kirsty Handley, who works in my team in Reading, did last year. So she ran all the convective cases from summer 2022 with a 300-meter ensemble. And so this is the sort of thing we saw. So this was a case, this is the radar, where there was this very heavy band of convection sort of somewhere in West London. And there were actually floods in West London on this occasion. And you can see that if you cherry pick an ensemble member that looks good, which of course is not totally a good thing to do, but bear with me, you can see that some of the members do look, well, they look very realistic. You've got sort of a sign of this very heavy line. And if you look at the equivalent in the 2.2 kilometer ensemble, which is the one we're running at the moment, you can see almost nothing. And so the organization is much better captured at higher resolution. And if we go to the probabilities, which is really the bottom line, so then you're using all the members of the ensemble, not just the one that looks quite nice, you can see that there's a very strong signal. So this is the probability of over 16 millimeters an hour rate of rain. And you can see that there's quite a good signal that there's going to be heavy rain over sort of London, whereas there's a much weaker signal in the conventional ensemble. So that's kind of one of the reasons we're interested in this, because this does show promise, but we have problems with it. So you move on to the next slide. So now I come on to WesCon, which is what you thought you were going to hear about all along, but that was motivational stuff. So WesCon stands for the Wessex UK Summertime Convection Experiment, which took place over this summer. This is a list of the main people involved. So these are people in the Met Office, and then there's people in universities involved as well, and one of them sitting in this room. And so you can see that this is the quintessential WesCon photo, as we decided it was, that this was taken out of the cockpit of the fan aircraft, and you can see the lovely green fields of Wessex and a variety of puffy clouds of different sizes, and one of them is big enough to be precipitating. And so this is exactly the sort of situation we're interested in. So marginally precipitating clouds, can we understand in the model whether they're precipitating or not? So move on to the next slide. So I wanted to say a little bit about why do we do field campaigns, because in a little bit more detail, because obviously this is very expensive. So you might wonder, you know, once we start flying aircraft around, it all sort of becomes quite a big undertaking. So why do we think it's worthwhile? Why do we really think it's going to be improving the model? So the bottom line is that we've lost the bullet points. The bottom line is that the models are complicated 3D representations of the atmosphere with potential for many compensating errors. And as I said earlier, the routinely available observations are just not sufficient to work out what's going wrong. If something's going wrong, there's a lot of reasons. And so you need bespoke observations. So I've got a noddy example of this if you move to the next slide. So this is very simplistic. So meteorologists in the room may well say, there's a lot of things I'm missing out here, possible sort of feedbacks, etc., that I'm ignoring. But this is just a sort of an example of the sort of thinking of why you need to worry about these things. So say, for example, the rain at the surface is wrong in your model, you know, so there's several possibilities why that could be. Actually, there's some that aren't on here, but so obviously one of the reasons is the cloud could be right, the production of rain in the cloud could be wrong. You could have something wrong with the microphysics in your model. They're not producing enough rain, or it could be that the cloud is wrong. So, you know, the cloud might be in principle producing enough rain, but in some way the cloud might be, incorrect. So if the cloud's wrong, why might the cloud be wrong? You know, so, well, obviously there's an updraft somewhere in the cloud, so it could be that the updrafts are wrong. And if the updrafts are wrong, well, there's several reasons again why that might be. So one of them might be that the profile is wrong, the initial profile in the atmosphere has got the wrong amount of instability in it, etc. Or it might be that the turbulence is wrong. So, you know, you're not sort of correctly constraining the updrafts by the turbulence. So at every stage of here, you really need to be able to understand what's happening in an observational sense. So you need to be able to measure and see if there's anything grossly wrong with the cloud, or grossly wrong with the updrafts, or grossly wrong with the profile. So that's the sort of thing that you need to do to try and unpick what's going on with the model. Because otherwise, if you're just looking at surface rainbow or something, you haven't really got a hope of understanding what's going on. So next slide. And this has evolved over a few years in the Met Office. So one of the things about the Met Office is we're part of a partnership with other Met services that use the same model as us, the unified model. Beth Woodhams and I were chair a while ago of the Convection working group, which again involves a lot of these different Met services. And we as a group, so I don't take complete credit for this, obviously it was the whole group did this, but you know, we came up with 3 priorities to take forward back in 2020, and one of them was 3D convective cloud evaluation, and Tor was in charge of that subgroup. And then there was another one which was idealized modeling, which isn't so relevant here, but then the last one was very much relevant to WesCon, which is understanding the deficiencies in the pre-convective profiles. So this was kind of a lot, in some ways, was the beginning of the thinking that led to WesCon, that we really needed something. And I should say that, you know, there have been field campaigns in the past, but the thing that's really different about this one is there's more of an emphasis on the sort of dynamics, so the velocities and the turbulence, as opposed to the microphysics, which obviously is also important. So if you move on to the next slide, so this is kind of an introductory slide to WesCon. So it's a very big campaign, happened from June the 1st to August the 25th, so over the whole summer, so 12 weeks over the summer. And the area that we're interested in is this area in red, which you might think is a slightly odd shape. So it's a very specific shape, you might think, actually. But the reason for this is that this is determined by the airspace constraints, so where we could fly the aircraft, which I'll say more about in a minute. So, for example, here you're near Bournemouth Airport, here you're near Bristol Airport, so this is probably why there's these indentations here. And so the bottom line was the Chilbolton research radar, which we were making use of, is fixed. So we wanted to fly somewhere where we could also scan the clouds with the Chilbolton radar. So the choice was, you know, we can't fly to the east of here because obviously it's too close to all the very busy airspace near the London airports. And so you have to really go to the west. So if you move on a slide, so this is where you come to the question of why it's called Wessex. And we know that, you know, Wessex is, you know, it's an old ancient English kingdom. We don't really refer to it, it's not the name of a county anymore. It's also associated with Thomas Hardy, who gave different names to all the towns in a rather nice way. But then if you move on to the next slide, obviously, Thomas Hardy never really thought of it as just the area west of Chilbolton. It's probably a very meaningful definition of Wessex. So if we move on to the next slide, which is the same as the previous slide. So we had both ground-based and ground-based observations and observations that were deployed during IOPs. So we had these are the routine observations we had, and I'll go into more details about a lot of these. But so we had a super site, a ground-based super site at Netheravon, which is an army base roughly there, which had various instruments here, particularly Doppler lidar, microwave radiometer, etc. Then we had radar super sites at Chilbolton and Lynham. So Chilbolton is there, as mentioned, and Lynham is just outside the area, but it can scan through this area. And then for IOPs, we had various platforms that we could deploy when the weather looked suitable. So 12 to 15, we flew the FAM aircraft, which I'll say a bit about in a minute. Lots of radiosondes, lots of UAVs, and we also had a motor glider. So if we move on, I will say a bit, oh, okay, so yeah, so the other thing is that you may have seen we refer to this as WesCon WOEST, and that's because there was another project running in parallel with or alongside WesCon. So WOEST stands for WesCon Observing the Evolving Structures of Turbulence. So this is a NERC funded project. So it's a moderately late stage in the development of WesCon. NERC and the Met Office agreed to have a joint program on turbulent processes to understand turbulent processes in the atmosphere. That program is called Parachute. I'll say a little bit more about that at the end. And so WOEST, the main thing that WOEST did, it did a number of things which were very exciting, but one of the main things it did was it enabled the use of a lot more radar to understand the sort of dynamical and turbulent processes in clouds. So, for example, you can find out where the turbulent regions are in the clouds by looking at the Doppler beam broadening, from the radar signal. So I'll say a bit more about that in a minute as well. So if you move on to the next slide. There are three radars that we made, well, three radar sites. So there was the Chilbolton radar, which is an S-band radar, which is the biggest steerable dish in whatever it is, the research community. There was an X-band radar based there. There was another X-band radar and Kepler based in Lynham, and then there was a Met Office recent radar here at Warden Hill. So with the three of them, you can do clever things by overlapping, and so you can see here the blue areas are areas where there's dual Doppler, and the red areas are where you can see them with three radars. And so the idea is you can cleverly get out 3D fields for the velocities and the turbulence by doing that. So that's a very exciting aspect of the program. So if you move forward another slide. So this is just some nice pictures of one of the X-band radars being moved from Chilbolton to Lynham. You can see that these things are kind of mobile. You can't use them while you're driving along, but you can move them, and then it was craned on top of a container so it could see a little bit further beyond the clutter, etc. So that's the sort of thing that went on. So if you move on to the next slide. So Paul Barrett in Exeter compiled this slide of the number of people involved in WesCon. It really was a very impressive campaign with a lot of people involved. So we had 10 institutions and 200 people at least involved. I won't go through all this, but there was, a large number of people doing different things, 60 people launching sondes, for example, and 20 people evaluating models, so not even involved directly with the observations. So move on to the next slide. So the observational priorities for WesCon are summarised here. So these kind of tie into things I've already been talking about, but just to be clear, and I'll go through these in a minute in more detail. The first one is really the pre-convective environment. So we need to know whether the profiles in the model before the convection starts are correct, because that can often lead to problems. And the interesting thing about that is if the profiles are wrong before the convection starts, there's not much you can do in your regional model about that. So it may be something to do with data assimilation in the global model or something like that. So it's very important to understand that. There was a theory that quite often the models have too much sin, which is convective inhibition in the profile, which makes it too difficult for convection to kick off. So that's the sort of thing that we wanted to understand. So the second one is the boundary layer structure. So comparing structures in the boundary layer with evolving clouds as they first initiate. And I'll say more about that in a minute. So next, and the third one is just the thing that I was mentioning a bit before, that using the aircraft and radars to understand the vertical velocities and the turbulence in clouds as they develop. And then later on, when the clouds get even bigger, you can't fly through them anymore, and so it just becomes just radars that you can use at that point. So move forward to the next slide. So what actually happened then? So that was all kind of preamble, so I can start to talk about what we actually did now and an early look at some of the results. So this is a summary slide we produced on the last day of the campaign. And you can see that the campaign fundamentally was very successful. We had 12 flights of the FAM aircraft, 16 flights of the smaller aircraft, which I'll say more about in a moment. I mean, there's loads of 25 days of actually actively scanning the radars, 350 at least radio sondes we launched, 120 hours of UASs, and we had all these other sites operating a lot of the time. So it was very successful. So we move to the next slide. So we can think about what was the weather like over the summer. Now this might be a bit of a sad subject for some people to think about, but so June was generally dominated by high pressure and easterlies. I remember showing this in WCD actually, because there was this unusual situation where the winds were easterly across the whole Atlantic. And so there were some big thundery events, but they were mainly at weekends, and we weren't operating the experiment at weekends, so that wasn't very helpful. But July and August made up for that quite well, because we had a lot of very cyclonic, as you remember, very cyclonic conditions with many opportunities for shallow showers. Fewer cases of very deep showers and warm plumes coming up from the continent, unfortunately. And so, but there were many, many showers in general. So it was actually quite a good summer for an experiment like this. I think it's true to say that the nation's loss in terms of a good summer was our gain to some degree. So if we move on to the next slide. So I can go through these priorities now. So the first one is the pre-convective environment. So these were sampled with the aircraft, the 2 aircraft, but primarily by radio sondes. So if we go on to the next slide. So this was, it's not very subtle. We just basically launched loads and loads of sondes when we thought there was an interesting day in the offing. So this is an example from, there's this nice website called Sonde Hub, which people pointed out to us during the campaign, that you can keep track in real time of what sondes have been launched. So this was a day when we thought there was going to be some interesting convection. It was 18th of August, 9 o'clock in the morning. And so you can see that from the various WesCon sites, sort of through the sort of certainly the eastern part of Wessex, we launched quite a few sondes. But in addition, we were able to launch extra sondes from Camborne down here and from Herstmonceux. So both of those normally only do, I think they normally only do 0 UTC, maybe, or just one do 12. Yeah, they might do 12, but on this occasion, I think they were doing 3 and 6 as well. So we got, you know, some extra data from those. And one of the nice things about the project was that certainly in the department here, there were quite a lot of students launching sondes, and so it gave them a bit of interesting extra experience, a sort of thing that they wouldn't normally do. And generally, a lot of these, there were various volunteers also from the Met Office in Exeter and other places launching sondes down in deepest, darkest Wessex. So if we move on to the next slide. So that's all I was going to say about that. So the next interesting thing is the boundary layer variability. That's a subject, as I mentioned, that we're very interested in, both from the 100-meter scale models and also from developing parameterizations. So if you move on to the next slide again. So this is an example of the sort of thing that you can do. So when the radars weren't actively scanning convective showers, quite often they were doing automatic scans of the boundary layer, which obviously means sort of presumably lower elevations, etc. So this is the sort of thing you could see. This is an example from Lynham, so from NX Pol 1. So you can see here that you can sort of see that there's these sort of roll or maybe cellular structures in the boundary layer, and that's exactly the sort of thing we're interested in. So these structures come from insects. So when you've got an updraft, it tends to suck in the insects and concentrate them, and so you assume that insects are passive tracers actually, which I don't know what the insects would have something to say about that. But anyway, you can see these quite nice structures. And so, you know, one of the interesting things with a very high resolution models is that you often get rolls in the boundary layer in those. And so being able to verify that is very exciting, because it's kind of one of the things you don't often get good verification of. So if you move on, so one thing about this is that you don't get any quantitative information about these updrafts in the boundary layer. So if you go on to the next slide now, so we were very lucky to have this motor glider from, I think it's from Jade University in Germany. So as you can see here, it's like a glider, nice big wings with a propeller on the front, Moses being on it, and it's very exciting. So, and in fact, there's a photo there of the clouds over Wessex, which you took. And so this did, well, this actually, the idea with this was that we could sample the boundary layer and really understand the magnitudes of things going on. So if you move to the next slide, so this is an example of one of the flights. So what we tried to do, I just found out immediately before this talk, this wind rose is wrong actually, it should be further north, but that makes sense, because what we tried to do was to fly a crosswind and a long wind, because if there's rolls in the boundary layer, they're usually oriented along the wind. If you're flying and measuring sort of vertical velocities as you pass through them, updrafts, then you'll see different periodicity in the long wind and the crosswind directions. And so we tried to either fly sort of cross shapes or these sort of rectangles most of the time. And so this is just an example of one of the flights. And you can see here that there's temperature and relative humidity trace. This is the altitude. So you can see most of the time we tried to fly probably about halfway up the boundary layer. The boundary layer top was probably around about 1.2 kilometers or something like that. So you can sort of see that we tried to fly, which is where you'd expect the maximum, if you're overturning the boundary, that's where you'd expect the maximum vertical velocities. And also going up a bit higher, just as a sort of sanity check. And so you can see here that this needs to be zoomed in a lot in the time axis, but you can see that it just gives you a rough idea of the magnitudes of the overturning, that you're getting overturning up to about, you know, maybe a bit over 4 meters a second, which kind of tallies with what you might expect. So if you go on to the next, okay, so the next thing for the boundary layer stuff is UAV operations. So we had 4 UAVs which were provided by Manapia. which is a company which specialises in making observations, meteorological observations from UAVs. This is a photo of one of them, and you can see this rather odd pole here. It's about 1 metre long, and it has a sonic anemometer on the top. And so the idea with that is to move the anemometer away from the rotors so that you don't get too much disturbance of the rotors, although I'm sure backing out the winds is still possibly more complicated than you might think. And just to give scale, that just gives you an idea. These are quite hefty things. So these are operated from either Chilbolton or 2 sites on the Salisbury Plain training area, which is a military area, which was important for the reason I'll say about in a moment. So there are 2 modes of operations of the UAVs. The first one was constant pheasants. So that is using 2 UAVs to keep a constant pheasant at a given height for many hours. So 120 meters, so you fly the UAV up to 120 meters, keep it there for as long as the battery's going to last, which is about 25 minutes, and then replace it with another one and bring the other one down and change the battery, etc. So it's quite labour intensive. But the idea with that is that, in principle, because you've got fast measurements of winds and temperature and humidity, you can measure the fluxes, you can measure the upward fluxes. And there's been some preliminary work done showing that it shows a lot of promise for measuring the fluxes. So you can, in principle, get the fluxes throughout the whole day at a given level, and you can, in principle, do more than one level, of course, if you've got enough of these things. And then the other thing, which was very exciting, was doing 2 kilometre profiles every 30 minutes. So that required a BV loss, which is beyond visual line of sight. So it's quite hard to get permission to do that with UAVs, but because it was a military area, then there was permission to do that. So if you move on to the next slide, this is just an example of the sort of thing you can get. So this was flying over, I think this was, well, this was on a day when we thought there might have been a sea breeze. We couldn't see very much, I don't think, but it just gives you an idea of the sort of thing you can get. That you can get these profiles up to 2 kilometres every half an hour. So this is the wind speed and direction, and this is the humidity. You can see there's some kind of signature of a growing boundary layer here. So that's very exciting, and that's something that certainly excited a lot of people involved in the campaign. So move on to the next slide. So the next thing is, obviously we had Doppler LiDARs. So there's one at Chilbolton. So this is the sort of thing you get from the Doppler LiDARs. So this is the, unfortunately this is a different day from the other one, so we can't compare them, but this is the backscatter. The backscatter is from aerosol in the atmosphere, so you get an idea again of how deep the sort of boundary layer is. And then also there's vertical velocities, because you can, there's Dopplerized, so you can sort of see how quickly things are. So if you're staring upwards with your LiDAR, you can see the vertical velocities as a function of time. And again, you can see that, you know, the vertical velocities are going up to about 4 meters a second. So that's kind of, even though it's probably a different case, that's kind of consistent that you're seeing about the right sorts of magnitudes. And also to make sense of this, you need the fluxes, and so the fluxes can be calculated from a flux tower at Chilbolton. And so you can see in this particular case, you can see that it's consistent that the fluxes are increasing in the middle of the day and decreasing as you'd expect. And it's kind of roughly consistent, but there's a bit of a funny point there, but it seems roughly consistent. So that's it. So move on to the next slide. And the final thing, sort of boundary layer thing, which we had, which was very novel. I haven't actually seen very many results from this yet. Actually, there's a picture missing. I think there's supposed to be a picture there. Is there a picture come up when you press it? Oh, that's it, right. So, so this was 3D cloud cameras. So the idea with this is you have a cloud cameras separated from each other by a few kilometers. And by comparing them as a function of time, the high resolution images, they have wide angle lenses, you can get, you can work out 3D information about the clouds. So again, that's only really works with quite shallow clouds, I think. So it's kind of, that's why I put it in the sort of boundary layer, sort of things just above the boundary layer. But you can see an example here. This was obviously over London rather than Wessex, because it was developed at Imperial College. But so, for example, in this case, they're sort of trying to match up what they think are the same clouds in these two images from different angles, so you can work out properties of the clouds from that. So again, I don't think we've actually seen very many results actually from that yet, but again, it's got a lot of potential to try and understand the structures and the spatial scales, etc., in the clouds just above the top of the boundary layer. So okay, so we move on to the next slide. So the next thing I want to talk about is the turbulent budget in convection. So the sort of dynamical properties of convective clouds. So with this, the main instruments we use were the FAM aircraft and the radars. So if we go on one slide, so you might want to just press that again, actually, I think there's more. So this is just a slide. So we use the FAM airborne platform, which is the UK Meteorological Research Aircraft. So this is operated by NCAS, which is the NERC Centre for Atmospheric Science. And it's a converted BAE 146 aircraft, and it's got lots of instrumentation on it. Although the main thing we really just used on the on WesCon was the Ames probe, which tells you the sort of velocities and the turbulence, etc. So if we move on, move on again, yeah. So the novel thing that we did really was to coordinate the aircraft with the radars. So this was one of the very exciting parts of the project, and one of the things that was definitely very new. So this is an example of the sort of thing we did. So this was a particular day. You can see the flight track coming in. So the aircraft is based somewhere near Milton Keynes, so it probably flew in from sort of over here. And so this was just partway through a flight. You can see. So this doesn't really make much sense if you see it on its own. It looks a bit crazy, but then you have to bear in mind that they're sort of flying through clouds as they see them. And so without seeing the clouds, this just looks like a bit of a squiggle, though you can see there is a definite pattern there. So what the idea was here was to combine this with the radar data. And so we have this battleships type grid. So you can see A to L and 1 to 6. And the idea was that the radar, people scanning the radar, scanning through particular sort of convective clouds, would tell the aircraft in real time, we're looking at a cloud in a particular square, and the aircraft would try and fly through that. And so the idea was that we get data from both the aircraft and the radar on the same cloud, and so they supplement each other quite well then. So if we go on, I can sort of explain a bit more. So this is an example. This is a very sort of small part of one of the FAM flights. I think we've lost this scale off the bottom maybe. So I think this is only a few minutes worth of data, well, maybe half an hour's worth of data or something like that. So this is a quick look from the FAM website. So they colour where they think they're in cloud grey and where they're out of cloud blue in a very imaginative way. So you can see that quite reassuring. There's vertical velocities where there's clouds, and much less vertical velocity where there's not cloud. And you can also see sort of the various sort of microphysical parameters, how much water there is in the cloud, etc. And again, that goes up when you're in cloud. Probably that is how they know that actually. So if you move on to the next slide, this is an example of the sort of thing we get from this. So this is looking at distribution of vertical velocities. So we can see that inside the cloud, you get much higher vertical velocities, as you would expect, in effect. And then what you can do is you can then compare it with the models. This is a bit messy. This was very preliminary work done on one of the test flights by Heather Moore. So you can see that this is the aircraft data. You can see by our first look here that there seem to be bigger vertical velocities in the aircraft data than there is in the models. So if that was consistently true, that would tell us something very interesting about what the model is doing. So move on to the next. So obviously what we wanted to do then is we wanted to scan the same clouds with the radar. So we do have cases where we've obviously got both. So the idea is that the aircraft gives you sort of a limited area, sort of where the sort of just where it goes through, what the vertical velocity and turbulence look like, and the radar can give you a much sort of larger, sort of more spatial kind of distribution. So the two things together will give you sort of a nice calibrated product. So this is looking at. So this is just an example where a particular cloud was picked out and was scanned from the from one of the radars. And so you can see here that this is the reflectivity from Kepler, which is a 9mm Ka band, and from Camera, which is the big dish, the big S-band dish at Chilbolton. And you can see that just the reflectivity tells you something about the concentration of the hydrometeors. And so you can see here that the clouds we're scanning through. So these are slightly different. These three are just slightly different angles through here. So you can see where there's sort of certain clouds that you can see. And then if you move on to the next slides, the next step is to then look at the Doppler velocities. So that tells you the velocities to and from, sort of away from and towards the radar. So you can see quite clearly that you've got sort of different regions with different velocities in the clouds, which is telling you quite a lot. And then if you go to the next slide, then this is the Doppler spectrum width, which tells you something about the sort of the turbulence in the clouds. Well, it can also tell you other things. So you have to do a bit of work to process it. But essentially, it's giving you a direct sort of measure of the sort of range of velocities in your radar volume. So yes, that's telling you something about the turbulence. So you can correlate that with what you're expecting from the aircraft, etc., and see whether it all fits together. So that's all processing work which is being done or is yet to be done, but it's a very exciting data set. So I move forward to the next slide. So the other thing we did for WesCon, as well as making all the observations, was we did modelling activities in real time around WesCon. So we ran another 300-metre ensemble over Wessex, so it's called the WMV for Wessex Model Variable Resolution. We ran a deterministic comparison of 2 different types of physics in the model. And then we also ran a regional coupled ensemble every week, so that's coupled to the ocean model, etc. So if you move on, so this is just a quick thing about the Wessex model that we ran. So we ran a domain which was essentially over the Wessex area, and the variable resolution bit was a lot larger. So if you move on again, so this is again similar to what I showed before, so I won't labour this, but similarly to before, you see quite a good indication, much better indication in the 300-metre model that you're going to get heavy rain. So again, it's looking quite promising. So move forward again. So one of the things we did alongside this was we ran what we call in the Met Office a test bed. So we ran, what we do for test beds is we have exercises where we look at the weather in real time. We get groups of people together, different group of people every week, to look at the weather in real time and assess models, etc. And so we had 5 weeks of WesCon. We had the test bed running in parallel with WesCon. It wasn't only working with WesCon assessment, it was doing other things as well. So you can see the 5 groups will be really, you can see it's partly virtual, partly in real life. And so one of the things that was done with this was we got the test bed to evaluate the WMV model, and the initial indications from that is that it's favourably received, so that's very promising. And so that was another thing that a lot of people got involved with. So it's another big thing that went on over the summer. So if we move on to the next slide. So we're almost at the end now. So the next steps for this campaign. So clearly we've got a huge amount of observational data. We're currently a lot of people are very busy collating and calibrating the data. And the next step is that the data will be used to understand and improve the models, as I was talking about. So we're in a very good position for this, because quite often with field campaigns, there's a bit of a feeling about who is actually going to look at all this data. Well, in this case, we've actually got, as I mentioned earlier, a joint Met Office and NERC program called Parachute, which has a lot of scientists who will be also with Met Office scientists looking at all this data and trying to use it to improve the models. And so this includes universities of Reading, Leeds, Exeter, Manchester, and also CEH. So there's quite a lot of people in the building here, for example, who are involved with that. And as I say there, it's focusing particularly on the things I've talked about that were of interest, so particularly on convection parameterizations in kilometre scale models and turbulence parameterizations in 100-metre scale models. So I think that's just about it, really. I've got some conclusions which are probably fairly self-explanatory. It's been a good campaign. I think it's been a good experience for everyone involved, and I think hopefully we've got a lot of really good data. So probably in another year or so's time, we can come back and say all the things that we've learned from the data. So thanks very much.
Humphrey, are there any questions in the room?
If I sort of nudge the model towards the observation to see what we get better.
No, we haven't done that yet. I mean, that's something we might do at some point. I mean, that is a technique you can use. I mean, obviously, with the ensemble approach, you have the advantage that if you're doing a case study, you can always choose the one that is closest to the observations anyway, which is a kind of poor man's way of doing a similar thing. But I mean, that's the sort of thing we probably could discuss doing at some point. Yeah.
How many field campaigns do you often have in the Met Office? How often do they occur?
I think they happen quite often, actually. I mean, I think, OBR, which is the part of the Met Office, which stands for Observational-Based Research, which is part of Foundation Science, they do a lot of field campaigns. So most times, most years, there are sort of fairly major field campaigns going on. So, I mean, obviously, not often on a particular thing. So the last convection field campaign we had, I think it was in 2013, I was known as Cope. So UK ones on convection don't come up very often, but there's a lot of others. So they just had one sort of looking at boundary layers in Spain, for example, and Met Office is also involved in various urban campaigns going on as well. So there's always quite a lot of things going on. So yeah, we have a dedicated group that does this kind of thing, and they ran most of the practicalities of the campaign. So it's sort of, yeah, it's very good. But yeah, I mean, it is a very important aspect of our work is to really have observational data to improve the models.
So you're saying join the Met Office and go to Spain for a field
Well, that's right,
campaign?
or anywhere. I mean, you know, people go all over the place. Yeah, yeah. A lot of people went to Sweden last year, whenever it was. Yeah, so.
I'll check if there's any questions online. Oh yeah, there's a question. Thanks so much for the presentation. Much useful details. Can I know if the chosen case in the field campaign mainly focused on convection, where the cases that mainly focus on relative emissions?
No, I think we mostly focused on convection. Yeah, I mean, there wasn't much focus on the stable side. So yeah, they're interesting boundary layers. Might not be the campaign for you.
Many cases, no, I kind of hardly the answer, but when a case it would always out into convection, not much really happened.
Yeah, I mean, we had cases.
Those are interesting.
We had cases both ways, which is interesting actually. So because we had a load of these cases where there were going to be shallow convective clouds, and sometimes they were weaker than expected, and other times they were stronger. So in a way, that's ideal because you can try and look at those and try and understand the differences between them afterwards in slower time.
Because I remember you and I fairly early on having the conversation. We actually should probably fly at least sometimes in the ones where we don't quite know if it's going to happen or not.
No, well, it depends what you mean by convection.
Really
Yeah. It depends what you mean. I mean, yeah, I think that's true. I mean, we didn't have a huge variety of cases in a way because it was always very relatively cool, showery, northwesterly set up for just about well, certainly 2 months. So.
Were you panicked in June when there's a lack of convection?
I mean, something's bound to happen eventually, isn't it? So, I mean, I think the main disappointment was in June. There were some quite big thunderstorms, and they all happened at weekends, you know, which is a bit frustrating.
Did you lose a lot of money in June by there not being anything to look at?
Not really, no. I mean, I think like things like
in
flight
some ways
hours in
it's
the
quite
aircraft.
good.
I mean, it was quite good in a way because we could ramp up all the procedures. But the thing I didn't mention was there was quite a lot of, you know, logistics, making sure everything was in the right place and having meetings all the time to decide what's going to happen in the next few days ahead, you know. And everyone was sort of brushing up their forecasting skills, and we were relying on the DGU, the Defence Guidance Unit, you know, to come up with briefings, etc. So yeah, I mean, I think it was quite good in a way that things sort of ramped up fairly slowly. But yeah, I mean, you can always have more cases. Oh, Carla's got a question.
You said weekends. Is there any real reason why you couldn't fly weekends?
I think it's just staff issues, and it makes everything up that much harder. You know, people are less willing to. I mean, in the past we have done stuff at weekends actually in previous campaigns. But I think it's just there's more emphasis on quite rightly on good work-life balance now. But it is a bit frustrating when you've got a big field campaign. Yeah. Oh, go on. Yeah.
Is this the end of the field project? Would it carry on another year? Or
no, it's the end of the field phase. So we might do a bit of extra flying in February or March. There's some spare time for flying. So if we get some interesting, obviously more cases the better. If we get some good looking days in February and March, we might do something. But fundamentally it's finished. And so we're in the phase of analyzing. We've got tons of data already. We've got a massive amount of data. So you can imagine what it's like. So I mean, obviously we've had a quick look at some of it, you know, but a lot of it hasn't even been properly processed and cleaned up. So there's a lot to do still.
I just wanted to clarify that a lot of the observations are routinely collected, right? So even if we weren't working on weekends,
that's true actually. You did have radar stuff, didn't you? So
and so we got some really exciting scans of the really big deep storms as well that people will still be able to use, and we will have still observed stable boundary layers if they occurred.
That's a good point.
Any more questions online? If not, another big round of applause for on three. Our next meeting is either in December or January, TBD. Thanks again. Fantastic.